Hi, I'm Ilya. I've been experimenting with this 3D printed robot for a while, and I posted a few videos before and get a lot of questions and some interest from different people. So I decided to make a longer video to show the whole process for the beginners, from the assembly of the robot to teleoperation control, dataset collection, and autonomous model training. So I hope you will enjoy it, and let's begin. Let's start with the robot. It's called Standard Open ARM100 and it's completely open sourced. You can find all the files and components needed on the project GitHub page. This model consists of mostly 3D printed components and 6 servo motors and 1 motor controller. 5 out of 6 motors control the movement of the robot and give them 5 degrees of freedom, while the last one controls the gripper. You can open and close it to grab different objects. The biggest advantage of this robot is, of course, its price. The total cost of all components, including some extra parts that needed to make it work, is around $130. That is much lower than many big robots out there. If you think about robots that usually used in research labs, they cost around a few $1,000s. If you think about the bigger industrial robots, they can cost $10,000. So this one, like $100 robot, allows you to do a lot of research and experiments with robotics at home. And even so, it's not as strong and precise as more expensive analogs. It's a great entry point for hobbyists. Printing time depends on your 3D printer. For me, it took about 20 hours to print all the parts for one arm. The assembly is straightforward and takes around an hour. You can follow the official instructions on GitHub or YouTube, and they're easy to follow. Alternatively, you can buy a pre-assembled robot online. I've seen a few companies selling them. You will pay a bit more, but it saves time and effort if you're not into 3D printing and assembly. On the software side, the robot is controlled with the LeRobot Library. It's developed by Hugging Face, one of the most well-known companies in open source machine learning. LeRobot is their open source robotic project, and I will be using it throughout this video. On the high level, the control of the robot is easy. As I said, it has 6 motors, so basically any position of the robot is just combination of the positions of these 6 motors. So to control it, we connect the robot to the computer using this motor controller, and the computer sends us the position of each particular motor. So for example, if you want to move this joint, it will send a new position to this motor and it will move to this position. Every motor has encoder. It means that at any given point in time, we can read and we can know the position of this motor. It helps it to be even more precise because we can implement PID control for this motor, and it will be after adjusting the position based on the signal and the actual position that this motor has achieved. But the bigger question is, how do we decide what to do? So how do we send these commands to the robot, and how do we actually do the control of the robot positions and the robot movements? Before we can use an autonomous algorithm to control the robot, we need to learn how to control it manually. So this first robot that I've shown you is called follower arm, and this is the robot that will actually do the job needed. But I also have a second arm that's called a leader arm, and as you can see, they are almost identical. So they have mostly the same components, they have the same motors, they have same motor controller. The only small difference is here. So the leader arm, instead of gripper, has this trigger and convenient handle. And the follower arm, of course, has gripper that can grab different objects. So the logic of teleoperation using the leader and follower arm is pretty straightforward. You connect both of them to the same computer, and you read data from the motors, read data from the encoders of the leader arm. Basically, if you move leader arm to some position like this, you read the positions of all the motors, and then send these positions as a commands to the follower arm. And basically this follower arm will move to the exactly same position and will mirror all the actions of the leader arm. It's pretty straightforward and intuitive way to control it. And yeah, let's look at it. Let's see how it works in practice. Okay, now let's look at the teleoperation in action. So here I have my leader arm and my follower arm. Both of them are powered on and connected to my laptop over there using this USB cable. I also started a teleoperation script from LeRobot Library on my laptop, and currently teleoperation is working. So whenever I move my leader arm, the follower arm mirrors all the actions. And you can see that it's doing it pretty well. I can move pretty fast, I can go far in all the direction, I can move the gripper, so it kind of works pretty well. And I should say that it's very intuitive. If you do it for like 5-10 minutes, you can learn how to complete simple tasks using this teleoperation. So for example, let's try to grab this ball over here. So you just take the leader arm and then control it and then grab it, and it's very, very easy. So literally just play with it for like 5-10 minutes and you will be able to do it. I think it's pretty popular way to control the robots. Yeah, I can confirm that it's very convenient. On the other note, there is a kind of drawback of this approach, because to control one robot, you actually need a second one. It basically doubles the price of your setup. Even more, if you think about it, we don't really need motors of the leader arm. We need only encoders of this arm to send the current positions of the motors to us. So it means that we kind of have double the price, and the most expensive part of the robots, that is motors, is not even fully used. So it sounds slightly bit as a waste of resources, but again, it's the most convenient way to do it. On the other hand, there is, because we don't need to use motors, there is an advice in the official guide to remove gears from the motors. And when you remove gears from the motors, there is no resistance inside the motors, and it's much easier to move them. And presumably it's like more convenient, but honestly, I was lazy to remove all these gears when I assembled my robot, and I think it was a good decision, because now the motors have some resistance. It means you can actually keep it in some positions and it stays like this, it's not falling down. So it's actually even more convenient. And I've seen some people complaining that they removed gears and now it's not convenient to control the robot because it's like feels a bit soft, unstable, and so on. So I personally don't recommend it, but again, it's up to you. You can always try. As I told you, the default and the probably most convenient way to control the robot is this leader and follower arm setup. But it has one main drawback, that you need two robots to do it. So it basically doubles the cost of the robot. This is why the community is constantly working on different teleoperation options. And one of them is developed by me, is using PlayStation 4 controller to control this robot. You can see this is just normal PlayStation 4 controller that connected to my laptop. And I can control the robot by either using arrow keys or using joystick or using some buttons to open and close gripper and so on. So I basically, instead of using leader arm, I can use this controller for everything. One drawback of this approach is that you need to implement manually all the limitations of the robot. Remember when I showed you the leader arm and follower arm, I told you that all the physical limitations of the leader arm are applied to the follower arm. So there is kind of no position that is possible for the leader, but it is not possible for the follower arm. It's not the same when you control with joystick, so this is why I implemented some limitations. For example, when robot hits the floor and I still want to go down, my joystick starts to vibrate and blink with this red or pink colors to tell me that it cannot go further. It also happens when I try to open gripper too much and so on. So it basically limits the movements that I can do. Another interesting thing that I implemented is some ability to go to preset positions. So whenever I click these buttons, robot goes to some preset positions that I defined in advance, and these positions can be adjusted. And it's also kind of useful because if you, for example, always need to go to the starting point whenever you teleoperate your robot, it's just very convenient. You press one button and you are in the starting position. And finally, probably not the most useful, but probably most fun thing that I implemented is control using accelerometer. So as you can see, this controller has accelerometer, and I can use the accelerometer data, so the position of the controller, to actually control the robot. So you see the gripper basically follows the movements of my controller. So yeah, this is just one of the alternative ways to control these robots. If for some reason you have only one robot and you already wanna do it, you can try to use it. Even so it's not part of the official library yet. But if you look at the community, then there are a lot of other ways that people are experimenting with. So I think I've seen all the possible game controllers being used for the robot control. Also people use just simply like keyboard, touchpad. Some people do even gestures recognition when you just show something with your fingers in front of the laptop camera and the robot is simply doing. So yeah, basically there are like a lot of different opportunities, a lot of different ways. I think at this moment, none of them in the official library, so you just need to go to the LeRobot Discord or just search for different forks and search for different implementations shared by community. Yeah, if this is what you want to try, then you definitely can find many different ways to do teleoperation. Before I got some questions about the limits of this robot, and the first question is about the reach. So this robot has reach about 40, a bit more centimeters, so it's distance from here to here. And as you can see, it doesn't have any problems of going the kind of whole way to the farthest point. So you also can rotate it 180 degrees. And it even goes backwards. I don't know why you can use it and why it can be useful, but yeah, you can even kind of operate on the other side of the robot. That is again probably not very useful. But yeah, basically it's completely without any problems. It goes the whole range and don't have any problems in extending very far. Another question that I'm getting from time to time is the maximum load of this robot. And to be honest, before this video, I've never even tried to test it. So I made a few tests and realized that it cannot lift anything heavier than 400 or 500 grams. I would say the maximum reasonable weight of the objects to work with is around 200 to 300 grams. So here you can see this bottle is like half filled, it's weight around 250 grams in total. So let's try to lift it using the robot. So I grab it, I lift it. It's actually can lift it and can operate it, so it's still fine. I would say it's a bit struggling. It's like shaking a little bit, but still can operate it. But when we extend it, it's can barely lift it. You see, it's kind of cannot lift it, and eventually it fails when the load is too high. So it means that this is the actual limit that you can use. So if you're operating on like around the robot and there is no like disadvantage in leverage, then you probably can operate with objects with weight like this, with weight around 200 to 300 grams. But in practice, for all other cases, I would recommend to use like 100 gram object or less. Robot doesn't have any problems with them, so you can go the whole range and you can easily operate with them. So just don't go for like very heavy objects. This robot is not made for them. It's also worth mentioning that there are different types of motors. Some of them a bit stronger, some of them a bit weaker. So default motors that is suggested in the official page, I use it in this robot. And it's slightly weaker than the motors that I use here. So here I actually, in this follower arm, I use the stronger motors, 12 volts and 30 kilogram torque motors. And yeah, so if you use the default ones, then they're probably even a bit weaker. So, and you cannot go above 200 grams for the default model. On the other hand, I've seen that company who makes these motors, they have another version, even more powerful, even like stronger than this one. So I guess you can experiment. You can buy the strongest, the most powerful motors, and probably you can experiment with power supply. Again, I'm not sure if my power supply is the best possible here. So yeah, you can experiment with them. I guess you can go and improve the robot to be able to lift up to like 400 or maybe 500 grams. But again, this is my guess. So I shown you what my robot can do. It's like 2 times less than this limits. But again, I think you can squeeze a little bit more power from it. But let's see. I'm not sure. If you experimented with stronger robots or you have some other results of benchmarks, please leave a comment and let me know what can I improve to make my robot stronger. Another question that people ask in comments is about jittering. So sometimes you can see this robot is like jittering during the teleoperation. It like looks like this. So basically when it's supposed to be stable, but it's kind of shaky, more or less like this. And yeah, I think it's a common problem and it's slightly random. Some people have it, some people don't have it. But if you do have, the best solution that worked for multiple people so far is to adjust the PID controller. So you should find a code in the LeRobot library that is doing PID control and try to adjust the P coefficient there. With like a couple of trials and errors, you can reduce jittering a lot. So this robot is fine right now. I don't think it's shaking, but on the previous iteration, the first robot that I made was shaking quite a lot, and this adjustment of the P coefficient actually helped. Up to this point, I was using this original configuration of the robot that you can see here. But the nice thing about robotics is that you can make changes not only on software side, but you can make changes on hardware side. And you can change your robot, you can change the configuration, you can replace some parts. And this is what I did. And most of my experiments and experiments in this video I will do with this configuration of robot that I use. So it's, I would say, 90% the same robot, almost no changes. The only big adjustment that I made, I replaced the gripper with this one because I prefer it more. I think it's a bit more convenient. It's symmetric and also it's transparent, more or less, if you look from this side. So it doesn't attract the view for some of the cameras, and it's nice. And also I added 2 cameras. So one camera in the bottom is like forward-looking robot point of view camera, and another is the wrist camera that is a wide lens camera that is looking at the gripper and helps to grab the objects more precisely. Of course, it's not the only available setup. So I would say the original guide of the library even suggests you to use your laptop camera or your phone camera for the first experiments. That is pretty good advice, so I would suggest to start from it. But if you want to run like more experiments, if you want your robot and your policies to work a bit better, I would definitely recommend to experiment with cameras. And especially very popular setup is having some wrist camera similar to this one. And of course, there are different ways how we can do it, and I'm not the only one who is experimenting with this robot and this configuration. I've seen in community many different developments. A lot of them are open sourced, so you can find some extra 3D printable parts like mounts for the camera or alternative versions of the gripper, or even sometimes people add like extra motor or like extra joint, extra wrist to the model, to this robot to add one more degree of freedom. So yeah, the only limit for this is your imagination. You can experiment with different setups, you can improve your robot, you can change your robot. And again, as I said, it's one of the funniest part of the whole robotics hobby. So definitely give it a try and try to make your own configuration that you will run experiments with. There are multiple ways how to train a robot to walk autonomously. But today I will talk only about the most probably straightforward one, that's called behavioral cloning. And it's subset of imitation learning. Basically, it works as follows. First of all, you can collect the data set where you teleoperate the robot and completing the some task that you want. And then you train machine learning model that tries to predict the next actions that the human operator will do. So basically, this model simply trains to reproduce the same actions, or predict the future actions that the real human operator will do based on some collected data set. So when you collect data set, you probably need to do it in the environment as close as possible to the one where you want to run it. So if you make some real world robot that's supposed to operate in the real environment, then you need to collect the data in the places that are very similar to the real world. But I'm doing it just for fun, so I'm doing it for my hobby. So I instead decided to organize some controlled environment when I can run some experiments. And here you can see how it usually looks. So I have my leader arm here, I have my follower arm, I have one extra camera on top, and this is the top view camera that provides some good strategic view on the whole area where a robot can operate. And of course, I have my laptop and 1,000 wires that connect everything together. So today, for the example, I want to show how to teach the robot to do a very simple task. I have these colorful caps and balls, and I want the robot to learn how to pick the ball and put it inside the cap. So to do it, again, I need to collect this simple data set of me teleoperating robot and completing this task. To collect data set, of course, you need to run some script, the dataset recording script in the LeRobot library. And when you do it, usually it gives you few seconds to set up the environment, to reset it. In our case, it means to put ball somewhere in this area and put the cap somewhere too. And then you can teleoperate the robot to complete this task. So in this case, I need to just teleoperate it, grab the ball, move it on top of the cap and drop it. So, and then return to the initial position. So this is basically one episode. Whenever we record this episode, you just click a button to indicate that episode is recorded. All the video and all the positions of the robots are saved at this moment, and you have a few seconds to reset the environment again. So you basically reset it, you put ball somewhere else, you put cap somewhere else, and repeat it again and again and again. For the simple task like this, you need around 50 samples for the training. So you basically need to repeat this I think 50 times. And as you can see, it's a very simple task. It probably takes 10 seconds to do. So yeah, it doesn't take too much time to collect the whole data set that will allow you to train the robot to do the same task autonomously. I can give some advice about how to set up the environment, but you always can just experiment and try different approaches and try the stuff that works for you. So first of all, try to just critically look at your environment and see what can go wrong and see what issues can happen and just try to fix it. So for example, I'm not sure if you can see it, but I do my experiments on this dining table in my Conda, and The surface of this table is pretty slippery and it's pretty reflective, so actually video, when you record this table, they're like very strange and misleading. So to prevent it, I first of all printed this chess-like pattern that is much more like contrast, and it's like much easier to recognize objects when you look at them on this like with this background. And I also use this silicone mats under both of the arms just to prevent some sliding, because as I said, it's slippery, and when I do like some sharp movements without this stuff, the robot can just slide to the sides. That it's not good. So again, just look at your setup and try to find some weak spots and fix them. It's pretty straightforward and simple. The second advice is about the camera setup. So make sure that your leader arm is outside of the view of all the cameras, because if you, for example, take this leader arm and put it here, such as the front looking camera can see it, then you'll have a problem. Whenever you record your dataset, in your dataset you'll always have basically video or like images of the leader arm, and instead of predicting something reasonable, instead of learning to recognize the ball and how to grab it and how to put it to the cap, your model will learn just to repeat after the image of the leader arm that it sees. So like instead of learning something reasonable, just learn to repeat the movements of this arm. And it will be pretty messy and it's not useful at all. So just make sure that your leader arm is not visible for all your cameras. Another advice that I find useful is to before you're collecting dataset, try to just run some teleoperation and look at the camera feed. So whenever you run teleoperation or recording dataset, you can see the camera feeds on your screen. So try to complete the task a few times without looking at this robot real operation area directly, but looking only at the pictures, looking only at the camera feed. And if it's not enough, if you feel that or like see that it's basically impossible to complete the task based only on this video, then probably your setup is not optimal. It's probably not really good. Of course, algorithms and people, they recognize images a little bit different, and sometimes it can even like better recognize some patterns than the real human. But again, if you think that video, the quality of video, the angles that you use are very bad for completing this task, then it makes sense to try to rearrange stuff and make it more convenient. So again, just makes sense that just make sure that that your camera feed, the inputs that actual model will consume, are enough to complete the task that you want your robot to do. Once the dataset is ready, you can visualize it. Here is an example of one episode. You can see the video feed from 3 cameras and the recorded positions of both the leader and follower arms. The leader arms positions are labeled as actions and the followers positions are labeled as states. When we train the model, it uses all of this information, past observations and states, to predict the next actions. While playing with the real robot is the most fun part, it's not always the most efficient way to develop a policy to control the robot. That's why a lot of research is done in simulated environments. They are cheaper to use and allow for more reproducible experiments. The LeRobot library has integration with a few of them, as you can see on the screen. For example, in the push-T environment, the two-dimensional robot needs to push a T-shaped block to the green target. In another Aloha environment, the real bimanual robot is simulated and you can complete simple tasks like passing an object from one arm to another or precisely inserting one object into another. If you want to develop a new policy or make changes to an existing one, it's a good idea to test it on some of these environments first. There are already human-collected datasets available in Hugging Face, so you can use them to train your model and benchmark your results against the state of the art. That's very convenient. The supported environments use common gem format, so more environments can be added in the future. The community is also pretty active, and you can find work in progress or unofficial implementations of new environments. Now that we've collected the dataset, either from the real world or a simulation, we can train the policy. The policy is the algorithm that controls the robot by taking observations and predicting the next actions. At its core, it's neural network making most of the predictions with some extra logic to help it learn and perform the task. The LeRobot library already includes several state-of-the-art algorithms like ACT, diffusion, or VQBet, all great for your first experiment. They come from different research groups and each has its own unique architecture and techniques. There is also Pi0, a more complex VLA model, but I won't cover it in this video. For beginners, ACT is probably the easiest policy to start with, so it's a solid choice for your first experiment. But most of my work is focused on the decoder-only transformer or DOT policy. I developed it myself, and at the time I'm recording this, it's not part of the official library yet. So now let's talk about my DOT policy. I have published a whole repository with code, logic, and rationale behind the model. I will not go into details, but I want to use it as an example of how the policy works. My goal was to create a very simple policy that is small and easy to understand if you have basic knowledge of deep learning. Right now you can see the scheme of the model on the screen. It's very simple. It takes the available observations, passes state vectors through linear projections, and all the images through visual backbone, and I use simple ResNet 18 to get to align dimensions of all input vectors. Then these processed input vectors, together with positional embeddings and positional encoders for targets, are sent into transformer decoder layer. And this transformer decoder layer then later predicts actions that we need to send to our robot. I also use multiple tricks to make training process more stable and increase success rate. All of these tricks are described and listed in the repository. A detailed discussion of the model and results is out of the scope of this video, but again, as I said, I wrote down all the details in my GitHub. You can find the trained models on my Hugging Face page. I tested the model on the two simulated environments that I mentioned before, PushT and Aloha, and you can see that I managed to achieve better results than the state-of-the-art algorithms. The success rate of DOT policy is higher than success rate of the previous sorter for these problems. At the same time, my model is much smaller in size. Again, you can see the number of parameters of my model is much smaller than of other models. So for the rest of the video, I will use it to show the policy in action, but if you want, you can achieve similar results with other models too, so give it a try. Even if you're not an expert in deep learning, you can still train the model. The LeRobot library comes with an end-to-end training script, and the typical training command looks like this. You specify the policy, the data set that you want to train on, and a lot of optional parameters for the dataset, policy, or the training process. I recommend to always use GPU. Even with GPU, training takes hours. On a CPU, it's almost impossible to finish in a reasonable time. The good thing is that this training script already integrated with weights and biases out of the box, so it automatically logs all the training metrics and the system information, so you can easily track the progress. If you're training in simulation and run an evaluation, it will also log the evaluation results and a video of your policy in action. For example, here you can see the results of my policy trained on the PushT dataset, achieving high success rate, and how it actually performs at different stages of the training. Once the model is trained, you can run it on the real robot using the same library. Just specify the model you want to use and the camera feed for observations. The library handles the rest. Here you can see the robot in action. It performed surprisingly well, considering it was trained only on 60 samples. I don't do any teleoperation, and the robot acts completely autonomously. The policy is also quite stable and adapts to changes. Even when I move the cup, it keeps working. Overall, the robot works reliably, but of course sometimes fails. Quite often it happens without any clear reason. One common issue is freezing. The robot works fine, but at some point it just stops. This happens because during training I often slow down or pause right before dropping the ball. The model learned this pattern, but since its prediction horizon is shorter than the pause, it ends up freezing. To fix it, try using a longer prediction horizon or a model that can better handle these pauses. Another issue is that the robot struggles to pick up objects placed at the far left or right edges of its working area. Most likely that's because I don't have much training data with objects in those positions. The model finds it harder to extrapolate beyond the areas it has seen. My advice is to include at least some training episodes with objects placed at these extreme positions. Try to use the entire workspace and full range of motion when collecting your dataset. Training a policy is an iterative process. You collect some data, train an initial model, and test it in real environment. Then you look for weak spots and fix them, either by improving the dataset, tweaking the policy, or adjusting training parameters. Each cycle helps you gradually improve the policy performance. Let's quickly recap what we've covered today. I walked you through the LeRobot library and how you can use this library to control these nice 3D printed robots, to do teleoperation, to collect dataset, train models, and run them autonomously. Of course, it's very beginning, so the library actually has much more capabilities, so I didn't cover reinforcement learning, the big foundational VLA models, and some other functionality and that is inside the library. And you also can use it to control much more different robots. So I would say that everything that I've covered is just the first step in the experimentations and should be the solid beginning, but you still can do much more. So keep exploring the library, also join the community, because there are a lot of discussions, there are a lot of ideas that people share with each other, there are a lot of experiments and videos that people show. So it's pretty interesting, it's developing extremely fast. Every couple of weeks there are new, fun and interesting things that you can try. So stay tuned. I will also experiment more. I will run more experiments. I will run more tests and post more videos with the results of what I do. That's it for today. I hope you enjoyed this video, and I strictly encourage you to try it yourself and start your robotics experiments as soon as possible. So if you have any questions or suggestions, you can always leave them in the comments, and like and subscribe, because I will share more experiments and more robotics video in the future. See you in the next one.